Hello all. Um, I welcome you all for the lecture on finite element analysis and constitutive modeling in geomechanics. So, in this particular course, I will be giving a guest lecture on constitutive modeling using ordinary CAMCLA and modified CAMCLA. So, hope you enjoyed these lectures, the previous lectures, and this will be on mostly on constitutive modeling and how will you use some of the well-known constitutive models like ordinary CAMCLA and modified CAMCLA to predict soil response. So, this is the layout of my contents. I will start with why we need constitutive modeling and some of the idealized stress strain responses. I will just give a brief overview on the linear elasticity, nonlinear hyperbolic models, and then I will just give basic tenets of plasticity theory and why it is important to have this sort of a nice framework which will be useful in modeling the soil response, and followed by the introduction on the CAMCLA models. I will start with ordinary CAMCLA and then I will move on to modified CAMCLA. So, this will be the contents of this lecture, followed by I will be giving one more lecture where I will be you will be seeing the predictions of these CAMCLA models and what are its limitations and advantages will be discussed in detail. So, okay, before going into why constitutive models are important, I will just give you what is, before going into that, like what is a constitutive model. A constitutive model is a mathematical framework which relates to physical quantities. So, in for our case, I think like we want to have some sort of a relationship between stresses and strains, right? That is our the models which we develop tries to relate stresses and strains. And why modeling is important? Because it's hard to model any complex structures, and if you want to simplify the problem, and instead of doing a lot of physical model studies, if you want to numerically solve some complex problems, we need to really go into modeling of any structure. So, we are trying to make it simplified and to solve some real world problems. So, the models which we choose should be so it can be very simple, also it can be complex, so it can be in a wide variety of ranges. So we need to choose an appropriate model based on our requirements. So, so the models can simulate a complex stress path, and these rigorous models are actually proposed based on the principles of mechanics. So, once these continuum based constitutive models are developed, this will be used in tandem with the numerical methods which has been discussed in this course on using finite element methods or finite difference methods. You can use these constitutive models and solve some complex boundary value problems. So, this actually gives an idea why the material models or the behavioral models are really important, right. So, how you will model geomaterials? So, that is the next important question which we need to ask, how to model the behavior of geomaterials. So, for that you need to have as you are seeing on the screen, you need to have three important framework. One is the experimental evidences. So, you perform a lot of experiments in the laboratories and understand the mechanical behavior of geomaterials, starting from as simple as a liquid limit test to a much complex directional simple shear test. So, you have a wide variety of laboratory tests which you can carry out and try to understand the behavior. And you also do a lot of physical model studies. So, again starting from 1G test, and you can extend it to a NG or a NG test using centrifuge models, and there also you try to understand the behavior. So, in the laboratory you typically do an elemental test, whereas by physical models you try to simulate the exact field condition, you try to replicate in like using a model studies, and then solve or similarly try to solve a boundary value problem, right. Additionally, we also do a lot of field scale studies, right. So, we use cone penetrometer test, flat dilatometer test, and pressure meter test in the field to understand the stress deformation response. So all these experimental evidences are key before developing any constitutive model, because this gives you a clear picture of how the soil behaves under complex stress paths, complex environment. Already the soil or a geomaterial is extremely complex. We will discuss about why it is complex in the later slides, but it is complex. So if you want to realistically model it, you need to understand and get all these experimental response from the laboratory. So that's one of the key aspect of before modeling any geomaterial. So once we get all these details, we go back, we will use a mathematical framework. So we use some classical theories based on plasticity, fundamentals of plasticity. We also use thermodynamic framework. So we use different mathematical framework to model this response. So here actually what you are trying to see is a spring which shows the which tries to predict the elastic behavior of a material. We also have a dashboard which will be useful for understanding the viscoelastic response of a material, and here you are trying to see a slider, because since the granular materials are made of a lot of individual grains, it can slide. So there is a frictional response that is taking place in the system. So you have a slider, you have a spring, you have a dashboard. This is a simplified system. So you can actually use there are a lot of complex simple models like linear elastic spring based models to viscous viscoelastic, viscoelastoplastic. So the complexity keeps on building up. So but we just go for a basic framework, mathematical framework, from where we can develop these models. Also on the right side, you see we try to use the fundamentals of plasticity, where you try to model any response using, and you represent the material response in a three-dimensional principal stress space. So you have an yield locus, you try to find a failure criteria for, which actually models the soil response, right. So you have a mathematical framework set, you have the experimental, from the experimental evidences you are having a mathematical framework. Now using these things, these tools, you try to formulate a constitutive model, trying to relate the stresses and strains. So once you relate these stresses and strains, you come up with a framework to model the response. So that will be inbuilt in a numerical schema, which I will be showing in the next slide, and you will try to solve any boundary value problem. So for example, what you are seeing here is a slope stability problem. So here again, when there is a slip that is happening, the soils tries to strain a lot, so it undergoes a lot of plastic deformation along the slip line, right. So and so you try to use the model which can predict the response much better. So you need to use an appropriate constitutive model to quantify the material response appropriately, or material response, and also the boundary value problem response. So here again you are seeing a foundation problem, right. So here again, when you are inserting a pile into a surface or soil, so what are the stresses that is getting developed? Those response you need to so these can be solved by choosing an appropriate constitutive model. So that's the important key, like how you are going to use all these evidences, framework, and try to develop a model and solve a boundary value problem, right. So on the screen you are trying to see a finite element framework, right. So you have a geometry. So for example, in the previous slide what you saw is a footing problem or a slope stability problem. You try to make the geometrical scheme of that particular model, and then you discretize and then generate the mesh, and once you do that, you try to initialize with some incremental displacement, right. So once you have this incremental displacement, you can actually update the displacement and you can find out the strains, and as you see here, the strains are related to the stress, right. Here is what you use some material models, real, right. So here you use material models or constitutive models. From stress you are trying to transform it to strains, and from there you can find out the element nodal forces, then global flow forces, then update the displacement, and this keeps on continuing until equilibration is reached, right. So, you try to solve. So, in a numerical scheme like in a finite element framework, this relation between strain and stress or stresses and strain is key, right. So, this numerical tool is using a mathematical framework which models the geomaterial response. So, in any or any finite element framework, when you are using different tools like Plaxis or Abacus, whatever tools you are using, the key part of any numerical scheme is the model which you are choosing, the constitutive model which you are choosing. So, we have to be very careful in choosing an appropriate constitutive model for the geomaterials, and especially what we are looking for. If you are looking for large strain problems, you need to choose a model which predicts the large strain response accurately. So, depending upon the problem, depending upon the material, you have to choose an appropriate constitutive model. Okay. So, here now we will just discuss about some of the idealized stress strain response that you see in any material system, right. So, for example, you try to see a linear elastic model, right. So, if you have a metal rod, you try to apply some tension. So, you will have a linear stress strain relation. So, it does not have an yield point, but as you apply some strains, it will exhibit some stress, right. So, this relation is sort of a linear, but this is not applicable for many material systems, because many material systems are non-linear and it is also elastic. For example, if you take a rubber band or something, and then if you try to stretch it, so the response is not linear, maybe sometimes it is non-linearly elastic. So, you need a different constitutive model to model this particular response. You can use Mooney-Rivlin sort of a hyperelastic models to model this particular response, right. So, again, other idealized stress strain plot is you have a linear elastic and a perfectly plastic response. So, your conventional Mohr-Coulomb failure criteria, we will discuss about what is failure criteria in the later slides, but so those sort of elastoplastic models, it's actually modeling an linear elastic initial part. After that, the behavior is perfectly plastic, right. So, but some materials exhibit a hardening response, some material gains strength as you start shearing more and more, and sometimes the material also shows a softening response. So, the material strength reduces as you start shearing at larger strains especially, right. So, you also see some sort of a rigid perfectly plastic response. So, if you have a bond between two particles and then if you try to pull those particles apart, there is a sudden breakage. So, there is a stress, but there is not much of a deformation, but once it breaks, the bond breaks, then it is like behaves like a rigid plastic. So, there is no stress, but the stress is there, but the strain keeps on increasing, right. Again, these are all idealized model, but many material system does not follow this idealized system, especially when you are dealing with geomaterials, which is extremely complex, right. So, a typical stress strain profile also has a linear elastic zone. You have an yield point, and then after the yield point, the material starts hardening, reaches a peak, and then it also starts softening, and then at large strains it might reach a critical state, right. So, critical state, and this is a peak stress state, right. So, okay, these are all idealized stress strain profiles, what you are seeing on the left side of the screen. So, on the right side you see a typical soil behavior. Why soil behavior is extremely complex? Because as you all know that the soil behavior is not linear, the behavior is non-linear, and also it is irreversible, right. So, once you unload and reload, I think the behavior is not reversible. It will not go back to its initial position, and you sort of see a hysteresis loop as you start unloading and reloading. You sort of see a hysteresis loop that is getting formed. That is because of some sort of a plastic dissipation that is happening in the material system, right? So you have hysteresis, you have irreversibility, you also have stress path dependency. What is stress path dependency? So when you perform a compression test, the material response is different. So you will have a different strength when you are performing a test on a soil specimen under compression, and you will have a completely different response. So the strength will be different, and the volume change responses also will be different when you are performing a test under triaxial extension conditions. You can also do test at different stress path. You can perform at simple shear test or different shear test. So you can transfer. So we will see in the next slides how to do a different stress path test, but under different stress path the material response is completely different, right? So again, that's why the soil behavior is stress path dependent, and also it's rate dependent. So if you do at a very small strain rate, the material response will be different. Also if you do at like very high strain rate, the response will be different. So in addition to that, you also have time dependency, right? So again, when you're doing an odometer or a consolidation test, you will see secondary consolidation that's happening over the period of time. So with time, I think the behavior also changes. So it's again a time dependent response. Again, the soil behavior is density dependent, which you all know, because a loose specimen behaves completely differently compared to a dense specimen. In a dense specimen, you will see a lot of dilation that's going on, whereas in case of a loose specimen, the material contracts, right? So that's, in addition to that, the material also is history dependent, right? It also knows what is the previous history, what is the soil which already has experienced some sort of a stress. So the behavior also depends on the stress history, the pre-consolidation pressure which it has already experienced, right? So with all these things, the complexity of modeling a soil behavior becomes even more challenging, right? So we have all these nonlinear irreversibility, hysteresis, stress path dependency, rate dependency, time dependency, density, and history dependency. So again, that the challenge lies in modeling, considering all these aspects, and then try to model the material behavior. So unlike any engineered material like steel or other concrete or other materials, this soil, a natural material, is extremely complex, and it's actually challenging to consider all these responses and model it, right? So in the next few slides, I will show you what are the various experimental techniques which you use to quantify or relate the stresses and strains, right? So you actually try to probe the stress tensor or probe the strain tensor, and then try to get some information, right? So conventionally we use triaxial conventional triaxial test you try to use in the laboratory, where you have a specimen and then you try to apply a confining pressure. So when you're applying a confining pressure, you are equating sigma 2 equal to sigma 3, which is the intermediate and minor principal stress are equal, and then you try to apply some deviatoric loading and then shear the specimen. So when you're actually doing it, so as you see here, this is your stress tensor, so which is having 9 components, right? Again, you have a strain tensor which has 9 components. So when you're actually doing a triaxial compression test, you're trying to probe sigma 1, sigma 2 is equal to sigma 3, right? So yeah, so the other shear components are 0, right? So you have a stress matrix where you have sigma 1, sigma and sigma 3, right? So you are actually trying to probe these stresses and then try to find the strain response. So similarly, you will calculate epsilon 1, epsilon 3, right? The other shear components are 0, right? So this is crucial in behavioral predictions using advanced constitutive models, right? So again, here using a conventional triaxial compression test, you can do a compression test. Also you can try to do some triaxial extension test and you also can do a constant P prime test, but you need to be extra cautious, and it's a bit complex. If you have an appropriate system which can apply these sort of extension as well as a constant P prime test, it will be easier. But conventionally you try to do a compression test, right? So these are the other various tests which you do to probe the stresses in the stress tensor. So if you perform a unconfined compression test, so the confining pressures are 0, you apply only the axial stress. So you are probing one stress component of a stress tensor or a matrix, right? Stress matrix. So this is a component stress matrix what you are seeing here. Of that component stress matrix, you are actually probing only one stress component, that is sigma ZZ. When you are trying to do a triaxial stress, as we discussed earlier, you are trying to probe sigma 1 and sigma 3. Also, if you are performing a true triaxial test, you can independently control sigma 1, sigma 2 and sigma 3 and try to understand its material behavior. So you are trying to apply a true 3-dimensional stresses, and then you can vary different stress path and obtain the response. Right. In this true triaxial test, again you are making the shear stress component 0. Right. You are applying only the normal stresses. Right. Again in odometer test, you are applying sigma 1, and then sigma 3 is nothing but k naught into sigma 1. Right. So this is your stress matrix. If you see all these stress matrix, you are not trying to probe the shear components. So if you want to probe a shear component, you either use hollow cylinder torsion testing apparatus where you try to probe the two shear components, or you try to use a directional simple shear where you can probe all the shear stress components, right? So the more stress components you are trying to probe, you will get better understanding on the material response under complex stress path, right? So again, the complexity of operating these devices also increases as you try to control more and more stress components, right? So you use all these techniques basically to understand the material response by applying complex stress path, right? So when you are using a conventional triaxial experiments, you either do a drained triaxial compression experiment or an undrained triaxial compression experiment. So when you are performing a drained triaxial compression experiment, you try to move on this. So in this P prime Q space, this is P prime and Q both are invariants. So this is the mean effective stress, and this is the deviatoric stress, right? So when you are moving on this particular line on the total stress path, it will be always making an slope of about 3. But if you are performing an undrained test, typically the material behavior starts here and then goes to an undrained instability state, and then again it contracts to reach a phase transformation state, and then reaches this quasi steady state before reaching the critical state, right? So it contracts, after that it starts dilating and reaches the critical state, right? So this is a typical response under drained and undrained condition, and also it varies depending upon the density, depending upon the stress state it is in, the mean effective stress that you are choosing. So typically this is how the response will be. And if you are doing this in the P prime Q space, you are trying to isotropically consolidate the specimen. After that, you are trying to shear the specimen and find the failure point, right? So if you want to construct the entire failure locus on this P prime Q space, you need to perform test at different stress path. That's what I was emphasizing on, applying different stress path to construct the failure locus, right? So when you are so you can also perform triaxial extension test to get a point here, and a constant P prime test, right? So as I said, performing triaxial extension and constant P prime test, you need to have a sophisticated equipment to control it, and also extreme care should be taken by applying the stress increments at every stages. But once you perform it, you will get a failure point at different stress path, right? This is under compression, this is at a constant P prime, and this is at extension conditions. So if you want to represent that, so what you are seeing is a two-dimensional representation of the failure or a yield surface, right? I will define what is yield surface clearly in the next slides, but assume that this is a failure point, right? So once you join all the failure points, you construct a nice failure locus, right? That is in P prime Q space. If you want to draw the same, construct the same failure locus in the principal stress space, right? Sigma 1, sigma 2 and sigma 3, you try to move on the hydrostatic axis, that is you are actually isotropically consolidating the specimen and you are actually moving on this particular point, right. So if you are performing a triaxial compression test, obviously the stress path will be not on the deviatoric plane or octahedral plane. So this is an octahedral plane perpendicular to the hydrostatic axis, right. So you have to project it back on this particular plane to construct the failure locus, right. So again, here we can probe only using conventional triaxial tests. You can probe, you can get 3 stress path easily, but if you want to construct the entire failure locus, you need to look out for other testing devices. So here I am going to show about the true triaxial testing apparatus, where you can apply multiple stress path by varying B. What is B? This B is nothing but the intermediate principal stress ratio, right. This is nothing but the ratio of sigma 2 minus sigma 3 by sigma 1 minus sigma 3, right. So B equal to 0, B equal to 0 means sigma 2 equal to sigma 3. So which is triaxial compression test. B equal to 1 means sigma 1 equal to sigma 3, which is triaxial extension, sigma 1 equal to sigma 2, right. So you have triaxial compression. So this is the octahedral plane or the deviatoric plane, which I have discussed in the previous slide. It's perpendicular to the hydrostatic axis. So after reaching a hydrostatic axis, you can actually apply a triaxial compression test and move on this particular line, right. Triaxial compression, sigma 2 equal to sigma 3. Similarly, if you are performing a triaxial extension test, you try to move on this particular plane and then just locate your failure point, right. So what is the different stress state in between? So this is one sector of the failure locus, which is about 60 degrees, and you perform triaxial or this is triaxial compression, this is triaxial extension. If you perform different stress path, you will get the failure point on the octahedral plane, right. Similarly, in P prime Q space, this is how you get the failure points, right. So you finally construct the failure locus. So again, this anisotropy cannot be directly quantified. You need to do other different types of tests to quantify the anisotropy, but at least like you will try to get the failure locus by performing tests at different stress path, right. So now you have the test data. Now you have to fit all these experimental results in a nice critical state framework, right. So this slide will just explain on what is the framework or what is this framework all about, and the entire soil response can be modeled in this particular framework, right. So in 1950s, Schofield, Roscoe, they've came up with a state boundary surface, which is in the 3-dimensional space, which is nothing but like you have the deviatoric stress axis, the mean effective stress axis, and the specific volume, which is nothing but the void ratio, right. You have these 3 axes, and the entire soil response, they try to like fit in all the experimental results in this particular state boundary locus, right. So this is a 2-dimensional representation of this 3D surface. So you see a tension cutoff, you also have a Horselev surface, you have a Roscoe surface, right. So this surface need not be linear, this can be curved depending upon the material, but all the stress or all the behavior will be inside, the entire response will be inside this locus, right. There is no stress state that can exist beyond this particular locus, right. There is an impossible stress state beyond this locus, but you can have any stress state that is inside the locus, right. So, this is again experimentally they performed a lot of experiments, and then they try to construct this failure locus. So, this is P prime versus Q space, mean effective stress and deviated stress space. Also, you can represent all these things in like specific volume and mean effective stress space, right. So, you have a normally consolidated line, a critical state line, and an unload reload line, right. So, you have this factor lambda and kappa, right. Beyond this normally consolidated line, you do not have any stress states are not possible, but so you try to relate this mean stress, deviated stress, and the specific volume, and try to come up with this 3-dimensional locus, right. This is called as state boundary locus. So, how did you arrive at this particular locus? So, you perform lots of triaxial drain test. So, you like isotropically consolidate the specimen. After that, you start shearing and reach a critical state. Similarly, for different confining pressure, you try to reach the critical state. This is by performing triaxial drain test. So, you just reach this failure points, connect it, and then you will get the slope of this line, which is nothing but m, right. This is called as critical state stress ratio m. Similarly, you can perform a undrained test, and then material contracts and reaches, right, critical state. So, again if you represent the same thing in specific volume P prime space, if you perform an undrained test, again undrained test, the volume change is 0, as you all know. So, the void ratio is constant throughout the test, right. So, it moves on this particular line with increase or decrease in mean effective stress and reaches the critical state locus, right. Whereas, if you are performing a drain test, I think the void ratio, the volume change happens, and then it tries to reach the critical state. So, this is your normally consolidated line, and this is your critical state line, right. Okay. So, you try to construct the entire response in this critical state framework. This will be useful when you are discussing your critical state framework based constitutive models, which are nothing but the CAM-CLE models, right. So, before going into the CAM-CLE based models, I will just give a brief overview on the elastic models, elasticity, and the nonlinear elastic models, right. So, as you all know, I think the material response can be modeled linearly elastically. So, you have a stress tensor and a strain tensor. So, again this is a second order tensor, that is why you are having two indices, and this is again a second order tensor. If you want to relate two second order tensor, you have a fourth order tensor, which is CIJKL, right. So, that is your stiffness matrix, and this fourth order tensor will have about 81 components. So, you have a second order tensor which has 9 components, and you have another second order tensor which is having another 9 components. If you want to relate it, the stiffness matrix will have about 81 components. Then you start using your stress symmetry, strain symmetry, and inverse relationship, and then you simplify it to have about 21 components in your stiffness matrix, right. Once you have this stress symmetry, strain symmetry and inverse relationship, you reduce the number of components. You can further reduce the number of components by taking the material symmetry. So, if you are using a material which is isotropic, then you will come down to only 2 components, which is nothing but the Lamè's constant, which is lambda and mu. So, this Lamè's constant lambda and mu are actually related, and you can actually determine this lambda and mu are related to your Young's modulus and Poisson's ratio, right. So, this is your Young's modulus and Poisson's ratio, right. So again, so the total stress tensor, any total stress tensor is divided into the volumetric part plus the deviatoric part, right. This is your volumetric part of the stress tensor, this is your deviatoric part of the stress tensor. So if you want to relate volumetric part of the stress to volumetric strains, this is your sigma kk is your volumetric stress, and your epsilon kk is your volumetric strain, right. If you want to relate the volumetric stress and volumetric strain, you have a constant which is called as bulk modulus. So again, if you want to relate the shear stress versus shear strain, you have shear modulus. Typically, since in critical state framework you use P and Q, so P this is P prime is equal to K into epsilon V, right. Similarly, Q is equal to 3G into epsilon Q. So this is the relation between mean effective stress and the volumetric strain, deviatoric stress and deviatoric strain, right. So again, we can write all these things nicely, but again you can see clearly that K is a constant and G is a constant, right. This is not, there is no pressure dependency, nothing. It's I think it's constant and the variation is linear, but as you all know that the soil response is not linear, right. So you need to bring in some pressure dependency to this stiffness values. So there comes some of the non-linear elastic models. So in 1970, Duncan and Chang proposed some pressure dependent models, right. So they try to modify the elastic stiffness by bringing in so they modeled based on the hyperbolic equation, and they brought in this pressure dependency sigma 3, right. So you have this equation, and you can clearly see that the behavior is non-linear, right. So this is RF is again stress ratio, and this is actually the RF value can be tuned such that the hyperbola is trying to model the ideal curve is brought down to the actual material response. Similarly, you can do it for the volume change response also, right. So this figure actually shows your experimental results are compared with some of the nonlinear models. So as you can see, the material sort of shows an hardening response, right. It keeps hardening, and even though this is a simple linear elastic model with pressure dependency, it can match some of the experimental results, right. So in certain material system, for example, if you have a soil which is containing some sort of reinforcement or some sort of a waste materials, it sorts of hardens, the material sorts of hardens with strain. So those sort of response can be modeled using this simple hyperbolic model, but it has deficiency. So there is no a term called yield. So and also the softening response cannot be modeled or predicted, right. So material usually has dilation. This particular model does not predict the dilation response, right. And obviously the anisotropic and small strain nonlinearity is usually neglected using this hyperbolic model. As you can see, the stress strain response is modeled very well. However, the volume change response, as you can see, the volume change response is not matching well with the model predictions, right. It's showing a contractive response and it's almost linear. But later, this is your original Duncan and Chang model, but later actually there are modifications to this original Duncan and Chang hyperbolic model, and they tried to predict the volume change response also fairly accurately, but still it doesn't predict the dilation characteristics because of its simplicity, right. So this is another simple pressure dependent nonlinear hyperbolic model. Okay, so before going into some more details on the original CAM-CLAIM models, I just wanted to introduce something on the basic tenets of plasticity, right. So till now, whatever the linear elastic model doesn't have any yield or failure, we don't define any yield or failure, nonlinear hyperbolic model also doesn't have any yield of failure. So we use a failure criteria which for simplicity, but I think I will discuss more in detail in this particular section on the various tenets of plasticity. Then we will go into the original Camclay and modified Camclay. Right. So we already discussed about elasticity. So this is your first tenet, which is elasticity, and usually for soils the elasticity is very small. So the elastic nature is actually removed, or the elastic nature is won't be there when the strain is more than 0.002 percentage, right. So again, after this the material response is mostly the plastic. There is some sort of a dissipation that is taking place, right. So once the material starts yielding, the point at which the material starts yielding is called as the elastic limits, and the behavior is predominantly plastic after this particular point, right. So this is the yield is an important yield or failure is an important tenet of a plasticity theory. So this forms the predictions which we will be carrying it out. Again, the next important tenet of plasticity is the flow role or the plastic potential, which describes the plastic deformation of a soil response, right. So again, to get a nice flow role or a plastic potential, you need to understand the volume change response. Again, if the material can be dilatant, the material can be contractile. So you need to understand how the material dilates or contracts using an appropriate plastic potential. Also, the material can harden, so the material gains strength with as you start shearing. Again, the material can actually reduces its strength once you start shearing. So those are the hardening and softening response that you typically observe. So once it reaches, so the material actually hardens, and then maybe it softens, and then at large strains it reaches a critical state, right. So when it reaches critical state, we can define it as d epsilon v is equal to the volumetric strain, incremental volumetric strain is 0, there is no dilation, d dilation is nothing but d epsilon v by d epsilon q, volumetric strain by shear strain, that is called as ratio of volumetric strain to plastic volumetric strain to plastic shear strain is called as dilatancy, that is equal to 0, and the stress dq is also 0. So these are the condition when the material reaches critical state, right. So once the material reaches critical state, then we can choose that to be a state of complete failure, right. So how will you represent all these things in a 3-dimensional space? Usually you use a principal stress space, an Euclidean space. You try to represent the material response. So you hydrostatically compress the material, and then you reach a particular point, and then perform your test, and then you will try to locate the failure locus on this octahedral or deviatoric plane, right. So you have a nice failure locus that is constructed here on the octahedral plane, and this will and this failure locus will be helpful in finding out an appropriate yield locus yield equation, right. Similarly, as you see here, when you are hydrostatically compressing, and then you are actually going on this line and then reach the particular failure locus, right. This failure locus is how you try to get this by performing a triaxial compression test, right. So you represent the yield on a principal stress space and try to get a failure equation, the yield equation. So what is yield? The material, once the material yields, it starts the recoverable deformation stops and the irrecoverable deformation kicks in, right, and then it starts accumulating, and there cannot be any stress state that lies outside the yield surface. So the yield is a stress state or a point that is shown here on a 2-dimensional space, right. So this is considered as an yield point, but in 3D it's like a surface. You're trying to see a failure locus on the 3-dimensional space, right, sigma 1, sigma 2, sigma 3 space. So, how to identify this yield? For example, if you perform an odometer test, you can see there is a change in slope. So, this is your NCL, and this change in slope will actually identify your yield point, right. Similarly, you can do an isotropic compression, you get an yield point, then finally you can join all the yield point to construct the failure locus. See, typically it's easy to locate as the slope changes in your stress strain plot as your yield point, but it's not that easy in case of a geomaterial, right. So, you won't see this sort of a nice bilinear plots in case of a geomaterial. So, you need to identify by placing different plots, for example, P prime versus specific volume plot, or deviated stress versus strain plot. From here you can identify the failure point or the yield point, right. So, what you are seeing on the screen are some of the classical failure criteria that has been given in past several centuries, in the past couple of centuries. For example, Tresca was the first one to come up with this failure criteria based on the maximum shear stress theory, and von Mises also provided a failure criteria specifically for metals. So, if you see Tresca's failure locus is it's not pressure dependent. Of course, the Tresca and von Mises failure criteria are not pressure dependent. That is why you can see a cylindrical failure locus in the principal stress space, right. So, it's definitely not pressure dependent, it's not I1 dependent. So, I1 or P prime. So, these are all invariants and it's not pressure dependent. So, this two failure criteria is generally applicable for pressure independent materials. So, the pressure dependency is not there for these two material systems, right. And for von Mises failure criteria, you see a circular failure locus, whereas in case of a Tresca you see a nice hexagonal failure locus, right, in on the octahedral plane. Okay, so these two are pressure independent failure criteria, whereas the next two failure criteria what you are going to see, the Mohr-Coulomb and the Drucker-Prager failure criteria, are pressure dependent failure criteria, because you can see in the failure equation you have a pressure dependent term I1, and here it is again sigma 1 and sigma 3, you can just make it as a mean effective stress. So, this is again I1 dependent, right. So, the difference between Drucker-Prager and Mohr-Coulomb failure criteria, again you can see since it is pressure dependent, you can see a conical failure locus on the principal three-dimensional failure stress space, and you can see a irregular hexagon in the octahedral plane for a Mohr-Coulomb failure locus, right. And you can also have, you can see the similarity between von Mises and Drucker-Prager. So, the failure locus is circular on the octahedral plane in both von Mises and Drucker-Prager failure criteria, whereas the failure locus is hexagonal in case of Tresca failure criteria, and you see a irregular hexagon in case of a Mohr-Coulomb failure criteria. This irregular hexagon is predominantly due to the material response. Again, the soil behaves differently in extension, right. So, that is why it is not an hexagon, it is an irregular hexagon, and you can see the strength in the extension part or the tension part is lower than in the compression part, right. So, again this Mohr-Coulomb failure criteria will have a linear failure envelope in a sigma tau space, but some material does not have this sort of a linear failure envelope. In that case, you try to use other models which can model this non-linear part of the failure envelope. So, these are all classical failure criteria, and you can use this for our for modeling geomaterial also. So, again you all know that the Mohr-Coulomb failure criteria is commonly used, extensively used in many solving many boundary value problems because of its simplicity. You need to know only two parameters, C and phi, in order to model this failure response, right. So, the next important tenet of plasticity theory is the plastic potential or the flow rule. So, the plastic flow usually describes the deformation of soil post yielding, and again, as you know, it is a irreversible process. So, this irrecoverable plastic deformation is described using the flow rule, and as you know, this is a kinematic assumption of this irrecoverable deformation, and you need to know the plastic strain increments for every stress increment. So, the direction which specifies the direction of the plastic strain increment is generally specified on the yield locus, and if the plastic strain increment coincides with the stress increment, then the normality condition is satisfied. We will discuss about the normality condition and the associated and non-associated flow rule in the next slide, but before that, to have this flow rule, you need to know what is a plastic potential function. So, this plastic potential function, if you want to get an appropriate plastic potential function, you need to have a good idea about the volume change response of the material. So, this is directly determined from the stress dilatancy relationship. For example, D, which is the ratio of plastic volumetric strain by the ratio of the deviatoric strain, plastic deviatoric strain. So, if you know the response of a material, especially the dilatancy characteristics, you can come up with a proper plastic potential equation, right. If you know the proper plastic potential equation, then using consistency condition, you can determine this particular plastic multiplier rate. It is a scalar quantity which is a function of stress, temperature and other internal variables. So, what is consistency condition? So, consistency condition actually describes that for any plastic deformation, the stress state is always on the yield surface. So, that is why you are using dF is equal to F. This is the failure equation. F is generally defined as failure or yield function, and G is called as the plastic potential function, right. So, we try to use this consistency condition. So, as there is a plastic deformation that is happening, the stress state is always on the failure locus. So, there cannot be a stress state beyond the failure locus. So, as plastic deformation, as strain that is getting accumulated increases, the failure locus actually expands, right. So, using this consistency condition, you can determine this plastic multiplier rate, and if you know an appropriate plastic potential, you can determine the plastic strain increment, right. So, this is key, and in some cases you assume the plastic potential to be equal to the yield locus. So, we will see when that is being assumed, but before that, as I said, if you want to get a proper plastic potential, you need to know the stress dilatancy characteristics. So, as you can see a typical stress dilatancy characteristics of a geomaterial, you can see as the stress ratio increases, the material contracts up to a point. After that, it starts dilating, it goes. So, the negative is the dilation part. So, it starts dilating and then reaches the critical state where the dilatancy is equal to 0, right. So, this is your typical response, and on the left you can see classical stress dilatancy equation that has been proposed by several researchers. So, the most famous stress dilatancy relationship which was provided by Rowe in 1950s. So, this is the stress dilatancy relation given by Rowe, and you can see how this predicts the material response, right. So, again the prediction is shown here. So, this is non-linear, and this response is similar to, you can see the actual experimental response, right. So, this response, this stress dilatancy response is somewhat close to this. We are also trying to compare it with the stress dilatancy relation given from Camp-Clay and the modified Camp-Clay. So, you can see a linear relationship is obtained in case of Camp-Clay, whereas a nonlinear relationship or nonlinear curve is obtained from when you are using the stress dilatancy relation of modified CAMCLA, right. So, we will see how to derive these things in the next few slides, right. So, this is on CAMCLA and modified CAMCLA. So, this is the stress dilatancy relationship, and using this you can get a plastic potential function, right. So, as I discussed, in some cases you can use f equal to g, right. Your yield function is equal to the plastic potential function. So, when you assume f is equal to g, this is called an associated flow rule, right. If f is not equal to g, then you have a separate yield function and you also have separate plastic potential function, and then you use it in the framework and then solve it. So, you have, so that is called a non-associated flow rule based models. So, this figure what you see on the screen actually represents the plastic strain increment which is plotted on the yield locus. So, if this plastic strain increment is normal to the yield locus, then it follows the normality condition, and if this plastic strain increment and the stress is in the same direction. So, this is the current stress point, right, and this current stress state and the strain increment are aligning with each other, then the material response is said to be coaxial, right. But as you know, the soil response is complex. So, your strain increment direction does not tend to coincide with your stress increment direction. So, it exhibits a non-coaxial response, which has been well established by many researchers. So, the soil exhibits a non-coaxial response. However, when the material reaches critical state, right, so the stress increment and the strain increments is almost following the same direction. So, it becomes a coaxial response at very large when it is under plastic flow state, right. So, this is again about the associated and the coaxial response that you would generally observe. The next important tenet is the hardening loss. As you see, when there is a work hardening material, the size of the yield locus expands as you start shearing. So, the material gains strength. So, if this is your initial failure locus, the failure locus keeps on expanding, right. So, you can have a separate hardening equation, or you can have an yield equation which takes into account the effect of hardening, right. So, again this hardening is defined as an increase in strength after yielding or when there is a flow that is happening. So, this is an additional plastic work that has been done, and this hardening is again classified into different types. One is the isotropic hardening, where you can see the failure locus actually expands in size. There is no translation, there is only expansion of the failure locus. Then there is something called as kinematic hardening, where there is a translation of the yield locus that is happening. You typically observe this sort of a kinematic hardening, especially when there is some sort of a cyclic response that is happening. So, when there is some shearing that is happening because of some seismic or earthquakes. So, that particular short term shearing sometimes translates this yield locus in a translates this yield locus, so that you can see or observe a kinematic hardening. Of course, there is some mixed hardening. The failure locus expands as well as it translates, right. So, you see all these different types of hardening under certain conditions, right. So, from this discussion on the fundamental tenets of plasticity, you have an yield equation, right. In our case, it is dependent on P prime, Q, P naught. P naught is the pre-consolidation pressure, and you have a plastic potential function, right. So, it is a function of internal variables P prime and Q, and you also have the flow rule, right. This is on the volumetric strain and this is for the deviatric strain. So, if you want to find this plastic multiplier rate, as I said, you have to use this condition f equal to 0 or df is equal to 0, which is the plastic consistency condition, and try to determine this d lambda. Once you have all these things, you can construct this compliance matrix, right. So, this is your compliance matrix. Once you construct this compliance matrix, I think you can, if you know the stresses, you can get the strains, right. So, now I will stop with this on the critical state framework. In the next lecture, I will be discussing on original CAM clay and modified CAM clay and its predictions.